Okay, so for today, we will be discussing principle of serological testing. Okay, so this would be the chapter outline of today's discussion. Okay, so our subject is immunology and serology. So it's actually two parts. So serology actually deals with the study of serum. That's the exact meaning of the word serology, no? We study the fluid components in the blood, particularly serum, because it is the serum that contains antibodies. And when we say serum, it is the liquid portion of blood minus the coagulation factors. So when you say minus the coagulation factors, minus fibrinogen. Okay, so it is the liquid portion of clotted blood because during the process of clotting, we remove fibrinogen. And why is serum preferred over plasma? Okay, so serum is preferred over plasma because it has no fibrin clot, no fibrinogen. And since it has no fibrinogen, it is optically clearer than plasma. And since it is optically clearer than plasma, then we prevent interference. I am not saying that we cannot use plasma, but it is preferred over plasma. So serum is preferred over plasma. So that is the reason why serum is the most frequently encountered specimen in immunologic testing. So we prepare serum by separating it from other blood component via centrifugation. Okay, so that's how we prepare serum. So ideally, we've used fresh serum that has not been heated. Okay, heating of serum refers to inactivation. So when you say inactivation, we are heating the serum at 56 degrees for 30 minutes. And the purpose of inactivation is to destroy native complement. Remember the complement system? The proteins involving complement. So the purpose of inactivation is to destroy native complement because complement may interfere with test results. Particularly if you are using the complement fixation test or if you are using if you are using doing the VDRL test. So complement fixation test and VDRL test. So these are the tests that requires inactivation. However, majority of the serological tests, okay, do not require inactivation of serum. So the ideal storage if testing is delayed is between 2 to 8 degrees centigrade for up to 72 hours. So if testing is delayed for more than 3 days, it is expected or it is ideal that you freeze the serum sample at negative 20 degrees centigrade, okay, for negative 20 degrees centigrade or below. Okay, this is for long-term storage. And if you will be getting liquid or chemicals from in the laboratory, you would be requiring, you will be using pipettes. Okay, so there are different types of pipettes. So, for example, the most accurate of them all is the volumetric pipette because it delivers only one kind of volume. So, this is an example. Can you see it? So, this is an example of a volumetric pipette. So, The label of volumetric pipette is 10. It says here 10 because this kind of volumetric pipette would deliver 10 ml. So all you have to do, you will be using an aspirator valve. You will be using an aspirator valve. So I'll just get, excuse me for a while. Yeah. You will be using an aspirator valve. And if you will be aspirating it, so the liquid is supposed to go, I hope you can see the marker here. The liquid will have to go to the marker here. Yan, I'm placing it in the camera. Okay. And then you can now actually, yan, thank you, Ma'am Gigi. And so this is the aspirator valve. So you will aspirate the liquid up to 10. And then before you adjust, you will have a tissue paper to wipe. And then you deliver. This is 10 ml. And then the graduated pipette has a graduation. Okay? So this is an example of the graduation. Okay, so it can deliver 0, 1, 2, 3, up to 10 ml because this is the capacity. Okay? So there are two types, serological and blowout. So for example, how would you know if it's blowout? So for example, it says here 9 ml. I hope you can see. Yeah, it says here 9 ml. So meaning to say, from this mark up to the edge, that will be the 10th ml. However, when you are transferring, there could be liquid, okay, that is not actually transferred. So you need to blow it out. Okay, so by doing like this. So you blow out so that the entire 10 ml will be delivered to the next tube. Okay, this is to blow out. Then the second type of pipette is this one, no? The micropipette. It can deliver small amount. So, for example, this pipette can deliver 100 microliter, 100 UL. Okay, so when you say 100 UL, that is equivalent to 0.1 ml. Okay, because 1,000 microliter is 1 ml. So 100 microliter is 0.1 ml. So that's how small the amount. Okay, so if you are using the micropipette, you will notice that this is the where you push the thumb. You will notice that when you push, then there's another. So the first push and then the second push. When you're going to aspirate, so this is now the pipette tips, no? So you get the pipette tip here. Sorry. So you get the pipette tip here, and then you can get materials, the liquid. So you just have the first push. And then if you're going to transfer it to another container, then you can push it up to the second push. So what's the purpose of the first push? First push, second push. First push is to aspirate. Second push is to deliver. The reason why some students are getting mistakes during pipetting is that when they aspirate, they are pushing up till the fullest push, 'di ba? So dapat try to I hope you can go to the laboratory during your face to face so that you can experience the first push and then the second push. The first push is to aspirate, then the second push is to deliver. And And if you will be removing the pipette tips, this is already contaminated with serum, so you do not touch it with your hands. You simply push it here. So see, look, you will push it here so that the tip will be removed automatically. So you do not you do not do it this way, huh? So you just push it here. See? Yan. So that's how you remove the tips, no? So usually up to 100 microliter, you are using the yellow tips. Okay? But between 100 to 1000 microliter, you can use the blue tips. So we have blue tips can deliver larger amount of volume. So we have another pipette for that, but I wasn't able to bring that in my office. Okay? So these are the different types of pipettes. Okay. So this is what I told you about. Use a mechanical suction. Okay. And then the purpose is to aspirate. So the purpose is to aspirate up until this portion, and then you wipe excess fluid outside the tube, outside the pipette, and then you deliver the entire thing. So if it's 10, it means that it can deliver up to 10 ml. Okay, so you drain into the receiving vessel. Okay, so this is the volumetric pipette. Okay, and then you should be able to read the meniscus at the eye level. So for example, this is the graduated cylinder, and if this is the liquid, okay, your eye level should be, the meniscus is where the line is, so that should be within the eye level. So you cannot read pipette above the meniscus or lower the meniscus. It should be within the eye level. Okay, so let's talk about dilution. If the solution is uh, too concentrated, we need to dilute it. Okay, so therefore, in the dilution, there are two terms that you need to understand. The first term is the solute, and the second term is the diluent. Okay, the solute is the material being diluted. So in serology, most of the time, we are referring to serum. Okay? Whenever we talk about dilute solute, we talk about, for example, serum in serology. Okay, diluent, or aside from that, it could be RBC. RBC can also be the solute. Diluent is the medium making up the rest of the solution. In serology, the most common diluent would be NSF, or the normal saline solution. Okay. It is preferred over water. Why? Because normal saline solution is made up of 0.85% sodium chloride. So it is made up of 0.85% sodium chloride, and it is isotonic. Meaning to say, it will not cause lysis of RBC. So it will not cause lysis of RBC. So the relationship that is expressed as a ratio or a fraction. Okay, so equations are being determined to determine the number of dilution. So usually dilution is computed using the total volume and the amount of the solute. Okay? So when we say total volume, we are referring to solute plus diluent. Okay? So total volume is solute plus diluent, then over the solute. Okay? So let's have some problem here, no? About simple dilution. Wait. Okay. So how do we know what is the dilution of 0.2 ml of serum in 0.8 ml of NSS. So let's say this is our first problem. So we have to determine first the total volume. So total volume is 0.8 plus 0.2 over 0.2. So, sorry, this is dilution pala. And this is the total volume. And then this is the solute. Therefore, the dilution is 1 over 0.2. And 1 over 0.2 is 5. So the ratio is 1:5. Okay, I hope that's clear, ha? Okay, so the dilution is 1:5, or it can be expressed as 1/5. But usually, in serology laboratory, we express it this way, 1:5. So the dilution of 0.2 ml of serum in 0.8 ml of normal saline solution, therefore, is 1:5. Okay. In serology, aside from simple dilutions, okay, in serology, aside from simple dilutions, we also have compound dilutions. Okay? These are made when large dilutions are needed, and it is required of several steps of making several smaller dilutions. Yung several smaller dilutions, we call it serial dilutions. Now take note that each tube here, okay, each tube here contains the amount of diluent in a blue dye. So let's say the diluent here is water, and then the solute is the blue dye. So in serial dilution, we serially diluted, okay, the blue dye using water. So what can you see? The dilution here is 1:2, this one is 1:4, this one is 1:8, 1:16, 1:32, 1:64, and the last tube is 1:28. So the question is, what is the most concentrated solution? Okay. What is the most diluted? Okay. So the most concentrated is 1:2. Because when you say 1:2, the amount of diluent, okay, the amount of diluent is twice as much as the amount of the solute. So that's what we meant by 1:2. Among the series of tubes here, what is the most diluted? So the most diluted is 1:128. Meaning to say, the original concentration of the solute is diluted 128 times. So there is 128 times more amount of diluent, okay, than the original concentration of the solute. So that's what we meant by 1:128. So how do we do this? So we simply prepare tubes, no? So there are about 7 tubes, right? So there are 7 tubes. Pardon me with the unequal amount of tubes. So let's say, for example, we place 0.5 ml of water in each of the tubes. So tube 1 This is tube 1, 2, 3, 4, 5, 6, 7. Tube 1 to 7 has 0.5 ml of water. Okay. And then tube number 1, we add 0.5 ml of blue dye. So we add 0.5 ml of blue dye in tube number 1. We mix it. So what is the dilution in tube number 1? So the dilution is total volume over solute. So it is 0.5 plus 0.5 over 0.5. So the answer is 1 over 0.5, and that is 2. So the dilution here is 1 is to 2. Okay, so what you'll do next in the serial dilution is that you transfer now another 0.5 ml into the second tube. So in dilution in tube number 2 would be still 1 ml, right? Because 0.5 plus 0.5 plus 1 ml. However, the solute is no longer 0.5 ml because the solute is, you divide the solute over 2. So instead of having 0.5 as the denominator, your denominator will be half of 0.5. And what is half of 0.5? So half of 0.5 is 0.25. So if we're going to 1 over 0.25, it's gonna be 4. So the dilution in tube number 2 is 1 is to 4. So I hope you get it, no? And then you transfer another 0.5 in tube number 3. And then you transfer another 0.5 in tube number 4. And then you transfer another 0.5 in tube number 5. And then you transfer another 0.5 in tube number 6. And then you transfer another 0.5 in tube number 7. And you discard 0.5 ml from the last tube. So that's how you compute for serial dilution. So if you're going to tell me what is half of 0.25, half of 0.25 is 0.125. So the dilution here is 1.0 over 0.125. So the answer now is 8. So tube number 3 is 1 is to 8. Now what is half of 0.25? Half of 0.125 is 0.125 over 2 is 0.0625. So 1 over 0.0625 is 16. So dilution in tube number 4 is 1 is to 16. And then you transfer another 0.5 ml. So for tube number 5, that's 1.0. And what's the half? What's the half of 0.0625 over 0.0625 over 2? 0.0625 over 2 is 0.03125. So 1 over 0.01325 is 32. So on and so forth. No? So that's how you compute for serial dilution. Okay? Okay, so that's how we compute. So tube number 1 is 1 is to 2. Tube number 2 is 1 is to 4. Tube number 3 is 1 is to 8. Tube number 4 is 1:16. Tube number 5 is 1:32. Tube number 6, 1:64. And then tube number 7 is 1:128. So this is serial dilution. So serial dilutions, first is that you have to plan the number and size of simple dilutions necessary to reach the end point. So we calculate its simple dilution and keeping the dilution factor at the same each step. So what do we mean by the dilution factor? So the one that you see here is an example of the two-fold dilution. In a two-fold dilution, um, you simply making dilution twice in each serial dilution per tube. That's what we meant by serial dilution. However, in the laboratory, particularly in serology, the most common types of dilution is the two-fold dilution. But in bacteriology, since there are many bacteria, the most common type of dilution is the tenfold dilution. Meaning to say, your first tube is 1:10, 1:100, 1:1000, 1:10,000, 1:100,000. So this is what we meant by the tenfold dilution. So the most common type of dilutions that we are using is a two-fold dilution and a tenfold dilution. Okay, so we have to set up the series of tube and we have to obtain the final dilution. Okay, so that we can determine the dilution factor, which is raised to a power equal to the number of tubes. Why is it important? So that we can determine the titer. Okay, so what do you mean by titer? The titer is the last tube in which a positive reaction is visible. Or a titer can be defined as a reciprocal of a highest dilution showing a positive reaction. And why titer is very important? Because titer is an indicator of antibody strength. Meaning to say, the titer is equivalent to the concentration of the antibodies. So that's why titer is very important. So, for example, you have here a specimen, no? 1:2, 1:4, 1:8, 1:16, 1:32. Okay? So, and then you test it for, let's say, an agglutination reaction. So, in 1:2, you see the agglutination is almost 100% of the field. So, we say it is +4. 1:4 is just like this. It's +2. 1:8 is like this, so just +1. 1:16 is no agglutination, it's negative. 1:32, there's no agglutination, so it's negative. So, what is the titer? The titer is the reciprocal of the highest dilution showing a positive reaction. So, the first thing that you have to know is what is the highest dilution showing a positive result. The highest dilution showing a positive result is 1:8. What is the titer? The titer is the reciprocal of a highest dilution showing a positive result. So, meaning to say, the titer is 1:8. The dilution is 1:8. What is the reciprocal of 1:8? The reciprocal of 1:8 is 8:1 or simply 8? So if I ask you, what is the titer? You should answer 8. If you answer, if for example, in this particular problem, I ask you, what is the titer? And then you answer 1:8, that is wrong. 1:8 is not a titer. 1:8 is the dilution. Dilution is different from the titer because titer is defined as the reciprocal of a highest dilution showing a positive result. Therefore, the titer is not 1:8, but it is simply 8. Okay, so that is the titer, no? So, for example, what is the importance of titer? Titer will allow us to determine increase in antibody concentration. So what do we mean, for example, four-fold increase of titer in convalescent stage? Pag minsan meron kayong nakikitang ganyan, what do you mean by four-fold increase of titer in convalescent stage? So for example, during the acute phase, the titer is 4. Pag sinabi nating four-fold increase of titer in convalescent stage, ibig sabihin kasi ng convalescent, the the patient has already produced antibodies. So if the patient has already produced antibodies, four-fold increase would be 4 times 4, which is 16. So it could be more than 16. So pag sinabi natin more than 16, could be that there is indeed a four-fold increase of antibody titer. Okay, so that's the importance of serial dilution. Serial dilution will allow us to determine the titer. Okay, I hope that's clear. Okay, so let's talk about test parameters. Okay, what is the importance of test parameters? Test parameter is important so that, for example, you have a new method. So test parameters will allow us to compare it with the gold standard. And when we say comparing it with the gold standard, we can determine 4 parameters. Okay? So we can determine 4 parameters. These parameters includes sensitivity, specificity, positive predictive values, and negative predictive values. What do we mean? So let's talk about them one by one. So when we say sensitivity, it is the proportion of people who have a positive, who have a disease or condition, and who have a positive test. Meaning to say, if I have COVID-19, whatever test kit that I'm using should be able to yield a positive result. Okay? So that's what we meant by sensitivity. No matter how small the amount can be, it can still be measured and it can still produce a positive test result. Meaning to say, you have you're able to get a true positive result. What do you mean by true positive? Pag sinabi natin true positive is that, for example, I use this kit to determine if I have COVID-19. For example, I really have COVID-19. By using the kit gives a positive result. So that result is true positive. What if the kit gives a negative result? Then that kit gives a false negative. Kasi meron talaga ang COVID-19. Yet, the test gives a negative result. So that is a false negative. So that's what we meant by sensitivity. When we say specificity, it is a proportion of people who do not have a disease or condition and they also have a negative test. So for example, I do not have COVID-19, but when this kit tested me for COVID-19, I am negative because I do not have COVID-19. Therefore, my result is true negative. Meaning to say, it measures the substance that it is designed to measure. It doesn't measure interfering substances. What if there is this test kit? I do not have COVID-19, but when I allow myself to be tested with that particular test kit and it gives a positive result, and yet I do not have COVID-19, then that kind of result is called false positive. So both false negative and false positive are inaccurate results. We do not want false negative. We do not want false positive. How about the positive predictive value? The positive predictive value is the probability that a person with a positive screening test result actually has the disease. So that's what we meant by um, positive predictive value. So it is computed by determining the amount of true positive over true positive plus false positive times 100. And when we say negative predictive value, it is the probability that a person with a screening test does not have the disease. So it is computed by determining a true negative over true negative plus false negatives. So let me give you a problem. Okay, I will give you an example. I will give you an example on how to compute. I will give you a method on how to compute for it. And later on, you will be computing uh computing for it in the sheet work that I will be uploading in the Brightspace. Okay. So you make a 4x4 contingency table. Okay, you make a 4x4 contingency table. So let's say, for example, this is the RT-PCR. RT-PCR is the gold standard, gold standard for COVID-19. Okay? And you have here the number of positive individuals with RT-PCR. You have here the number of negative individuals with RT-PCR. And then on the other side, this is the method, the new method, okay, the proposed new method because nagtitesis ka and you discovered that you have found a new method, okay? So you have here proportions who are positive and you have here proportions who are negative. Therefore, the number of individuals in this first quadrant is, let's label it so that we'll not get confused. Let's label it as A. And then here, let's label it as B. And here, let's label it as C. And then let's label it as T. So letter A is the quadrant of the true positive. Meaning to say, these people have COVID-19 and they are tested positive in RT-PCR and they are also tested positive in the new method that you are proposing. Remember, if you are proposing a new method, you have to compare it with the gold standard. And in this scenario, let's say that the gold standard is RT-PCR. Now, letter B is the people who got false positive result. Why did you say false positive? Because these people, okay, do not have COVID-19 because they are negative in RT-PCR, yet in the method that you are proposing, they get a positive value. Therefore, these people is considered to be as false positive. Okay. How about letter C? Letter C is the people who get false negative. What do you mean? It means that these people are positive with RT-PCR. Okay? However, in the proposed new method of test that you are doing, these people get negative result. So, this is false negative. And letter D is the true negative. Okay? True negative. What does it mean? It means that these people do not have COVID-19. And since they do not have COVID-19, they are tested negative in RT-PCR. Yet, in the proposed new method that you are trying to propose, let's say, to the government, okay, you also get a negative result. So indeed, that is a true negative. Okay, so to compute for sensitivity based on the equations that we have discussed, so it's gonna be A plus C times 100. So that is your sensitivity. True positive over true positive plus false negative. Now, to compute for a specificity, so the equation would be D over D plus B times 100. So meaning to say, you get the proportion of true negative over true negative plus false positive times 100. And then, when you want to compute for positive predictive values, okay, so the equation that you'll be using is A over A plus B times 100. Meaning to say, you get the proportion of true positive over true positive plus false positive times 100. And if you want to compute for negative predictive values, then you can now compute it using the equation D plus C times 100. Meaning to say, true negative over true negative plus false negative. So that way, you'll be able to compute for the negative predictive values.